We're going to talk about simple harmonic motion, and it's not covered in the textbook, so I decided to do the recap this lecture that I did on the 24th of January in semester 1. Right, so we're going to talk about simple harmonic motion. So it's written here, simple harmonic motion, or SHM for short. And what simple harmonic motion is and why it is important is because it is the fundamental of vibrations. Right, so we know that everything vibrates. The engine in a car causes the car to vibrate. Just similarly, the wind going over the wing will cause the wing to vibrate on an aircraft. And all these vibrations exhibit something called simple harmonic motion. So it's important that we understand the fundamentals of it and where it came from. And also when you hear the term as you're moving forward, you will know what it is we're talking about. Alright, so simple harmonic motion, we could define it as a type of motion where the acceleration of the body, so whatever it is vibrating, we consider that acceleration of that body is directly proportional to the distance from a fixed point or an equilibrium point. Right? So for example, if we have a ruler on one hand, right? So imagine we have a ruler, right? And we clamp it on one end and then we were to pluck the end, meaning that we just flick it, right? So you could try it on your own, then it will vibrate up and down. Right, so you'll be going through some equilibrium position. And we're saying as it moves up, for example, it will move up fast and then eventually it will slow down, come to a rest, and then it will move back down now to our next position here. Right, so the fact that it's moving and slowing down and coming to a rest and then accelerating, it means that acceleration is happening. And that acceleration is always directed to the center or the center line or some fixed point. So when that is happening, we say that we have simple harmonic motion. We have this written here. Acceleration is directly proportional to the displacement. The displacement meaning that distance. Right, so we're going to look at a spring. And the reason why we look at a spring in so much different elements is that in most mechanical structures, it can be broken down to a mass. Right, a mass is like whatever it is, body it is. Right, then we have a spring. And then we have something called a damper. So we're not looking at a damper right now, but we're looking at a mass and a spring. Because if you were to think about any object, I think about that same ruler you may have in your hand. You could flex it, right? So it has some springiness, some elasticity. So that is the spring element, right? So if you were to balance or if you were to clamp the ruler and you put a weight on the end of the ruler, it will sink down, right? So that weight will be your mass, obviously. Right, so we could model almost all structures. Even in agriculture, we could model a mango hanging from a tree. The mango being the mass, and the stem the mango hanging from. If you were to pull on the mango, you remember the branches bend a little bit like a spring, and if you let it go, it will fling back up. Right, so that is simple harmonic motion, and we can model it as a mass and a spring also. Right, so we're looking at a spring. Right, so we have a spring by itself here. So we're looking at this picture here. Right? And then the next step now, what we're doing, we're going to hang a mass on it. So this here is a mass. Right? So let's make it a little clearer here. This is a mass, M. Right? So when you hang a mass on the spring, of course, it's going to deflect by some amount E, given here. Right? And we could recall Hooke's law. Right? So you remember what Hooke's law is? Hooke's law is the force in the spring is equal to the spring stiffness by the displacement. Right? So if it is you were to hang a mass, right, the mass now, the force exerted by the mass is what? M by G. So from Hooke's law, we could say mg, which is the force from the mass, is equal to k by the extension of the distance it extends by is E. So we could say mg is equal to E. That's Hooke's law. Alright, so take to the next step now. So the mass hanging on the spring now. So what we want to do now, we want to pull on the mass, just like how we pull on the mango. So we pull on the mass now. Right, so we stretch the spring more by a distance x. Right, so from the equilibrium or the initial position, it's stressed by X. Right, so now we could look at the Hooke's law now in this sense now. So we're gonna resolve forces. And in order to do that and understand how we're resolving forces, we're gonna draw something called a free body diagram. Right? And this is something that you will have to draw moving forward. And anytime you're dealing with a force or trying to figure out how force is acting on an object, it's always good to draw a free body diagram. And what it means is that we take our body and we take it away from its system. So we take the mass from here and we draw it separate. So free body and diagram. And we take that mass now and then we could draw forces on it. Right, so if you look at the mass here, the forces we have is on top here we have remember the spring trying to pull back on it, right? Remember you pull on this thing. So the spring pulling back up on it. So we're using Hooke's law again here, so it will be F is equal to Kx. Well, in this case here, X will be, well, X plus E, because remember it have X here, and then you have a little extra distance here, E. So it will be this plus this. Right, so that's the force that pulling up. The force that acting down is your weight, your gravity, which is mass by G, gravity. Right, so we could say now that, alright, because we have, just assume our position is moving, our direction moving, you could say moving down is positive. Right, so we could say mg is positive, and because it's acting in the opposite direction to the direction it's moving, we could say it's negative. So it will be minus and that force. That, and you could recall, remember we say Newton's second law. It was F is equal to ma, and this is here is F was a resultant force. Right, so we resolve forces, that's what we just now did. The down force minus the up force. And we say now Newton's second law is equal to ma. Right, so this is our equation here. Right, so we could expand the equation. We have kx, ke. Right, so we just expand it, we do some maths. And now we have ke here. Now remember ke is equal to mg. So if we bring the mg here now, then we will have mg minus mg. So that will cancel, so we end up with this. Right, so we end up with ma equal to minus kx. Alright, so remember A is acceleration, and remember what acceleration is. Right, velocity is dx dt, and therefore acceleration is d2x dt squared. Right, so all this is recap. Right, so that's what we have here. A is equal to dx d2 d2x dt squared. Right, so we go up here now. Right, so I just recall what we just now had downstairs here. We had ma is equal to minus kx, and we say m d2x on dt squared is equal to minus kx. So then what we could do, we could just bring the m across here. So that's what we did here. So we have d2x over dt squared is equal to that. Alright, so now we end up with this term, and we could summarize this, and we could call this component here, we could say call that omega squared. So we could say omega squared is equal to k on m. Right, so omega is root of k on m. Right, so this equation here is the equation for simple harmonic motion. So that's the mathematical equation that represents simple harmonic motion. So if it is, we say like a mango hanging from a tree exhibits simple harmonic motion, well then if we were to model it, right, and this modeling, mathematical modeling is this here. When you resolve forces and stuff, and you get an equation, you call it a math model or a physics model. Right? So that model, if you get the equation, looking like this, where you have acceleration is equal to some kind of constant by x, then we say simple harmonic motion. Right, and the reason why we do this here to get this omega squared is because this term is something called the natural frequency. Right, so this here, omega, is called the natural frequency. And the natural frequency is the frequency of which an object would oscillate if it is left to oscillate on its own. So for example, if you pull on the mango, you pull, you try to pick it, but it's picking, so you let it go. And then it will oscillate up and down a little bit, right? Just like the mass on the spring here. Right? So nothing causing it, holding it back, but it will oscillate at a certain frequency. So that frequency is called the natural frequency. Right? Think about a pipe. The way they say take a steel pipe or a piece of steel. Right? So we have a piece of steel and we hold it in our hand, we hit it on the wall or something. You will hear ping and it will vibrate, right? Now remember, it vibrating in the air, it vibrating free. So that free vibration, that sound you're hearing, the frequency of that sound you're hearing is the natural frequency. Right? So it are different ways to calculate that frequency. Right? But what we just now did when we obtain this equation here is we find the natural frequency of this system here, a spring mass system. So the natural frequency of a spring and a mass is given by that here, the root of the stiffness over the mass.